Oh, no worries. Cool. Do we start from the beginning or? Okay, cool. Yeah. So without further ado, our speaker today is Alex Wein, who is a postdoctoral fellow at NYU, and he will be presenting sub-exponential-time algorithms for sparse PSA.
Great, thank you so much. I'm glad to be here. So this is joint work with Afonso, Yunzi, and Tim. And so as some high-level motivation for the types of things I'll be talking about, let's imagine that we have some kind of a large noisy data set and we want to extract some kind of a hidden signal. So this can take various forms. So just a few examples could be finding which genes cause a disease, finding communities in a social network, predicting who will click on what ads, and so on. And all of these are high-dimensional problems which share a common feature that there are many, many possible solutions. For instance, if there are n different genes and you're looking for the k important ones, there are n choose k possibilities, which is exponentially big for large k and n. And similarly, there are 2 to the n ways to partition a network into 2 communities, and so on. And so naively, if we want to take this data and find the hidden structure, we might think that we need to check all of these possibilities. But of course, this is way too slow to be practical. And so we would like to know whether there's a smarter algorithm that can find the solution efficiently, say in polynomial time. Right, and so this is sort of the high-level goal of what I want to talk about, is developing a theory to understand which statistical problems are easy and which ones are hard. So I want to start by talking sort of at a high level about statistical versus computational trade-offs in these types of problems. In particular, I want to talk about something I call the low-degree method, which is a way to try to understand these. So what do I mean when I say statistical to computational gap? So let's just illustrate this by the canonical example, which is a problem called planted clique. So what's planted clique? We're going to make a random graph. So take n vertices. Each of the possible edges occurs with probability 1/2. So this is the GN 1/2 Erdo-Schrödinger graph. But then I'm going to pick k vertices at random and plant a clique there. So that means I connect all of those to each other. So this is now a graph with a planted clique. And the goal is that I give you this graph with the clique not labeled, and you have to try to find the clique. Okay, so this is sort of a very fundamental question in high-dimensional statistics. So what do we know about this? Well, statistically speaking, I can find the clique so long as its size exceeds 2 log n. And that's just because 2 log n is the size of the biggest naturally occurring clique in the random graph. But here's where things get interesting. If I want, in order to do that, I would naively need to check all the possible cliques, and there's too many of those. And if we restrict ourselves to polynomial time algorithms, we only know how to find the planted clique if it's way bigger than that, if it's like square root of n. So as k, as the size of the clique increases, this problem goes through different phases. First, it's just impossible by any algorithm. Then there's this hard regime where you can do it by brute force, but we don't know any efficient algorithm. And then finally, it's easy, meaning that we know polynomial time algorithms. And this is like a very general phenomenon. All these other types of problems also exhibit similar statistical to computational gaps.
What causes the gap in statistic time and computation time in this particular scenario?
Right. Yeah, that's a good question of sort of what causes it. Often, generally speaking, it has to do with often problems that involve some kind of sparsity have this phenomenon because naively you need to sort of check all the possible sparsity patterns in order to find the solution. But yeah, that's like kind of that question is precisely what I sort of hope to try to answer in this line of work. Because yeah, that is a great question of like what exactly makes things easy versus hard.
I'm sure we'll
And
get to
so
that.
I'll yeah, hopefully it will become maybe a bit more clear later. Yeah. Cool. So somehow this is different from the standard theory of NP hardness that you might have heard of, because here we're talking about average case problems. So planted clique is not the type of problem where we know how to, prove that it's hard condition on something like P versus NP. Average case means that the input is random instead of just worst case. And so this is the question that you asked, and the question I also would like to ask is what fundamentally makes problems easy versus hard? And so, okay, how do we, if we think the problem is hard, we haven't been able to find a better algorithm, how do we really prove it or attempt to prove it? So, it's beyond current complexity theory to actually prove that things are hard, but there are various forms of rigorous evidence, so-called, that people have looked at. So there's, a big list of possible things you can, concrete things that you can prove in order to argue that something is hard. There's reductions between different average case problems. There's certain structural properties of the solution space that imply that certain algorithms have to fail. Perhaps you've heard of the statistical query framework or the sum of squares framework. So many different possibilities. In this talk, what I want to focus on is something called the low degree method. And this was introduced in a series of works that are listed here by all of these authors at the bottom. These papers were looking at the sum of squares hierarchy, and this low degree method is something that sort of evolved out of the sum of squares hierarchy. And so let me try to jump in and explain, what I mean by this low degree method. So suppose we want to just hypothesis test between two distributions. So what do I mean by this? One distribution is going to be what's called a null model, which in the case of planted clique, you can think of as just being a pure random graph with no planted structure. And the other distribution will be a planted model, which is where you have the random graph with a planted clique in it. And instead of thinking about the question of trying to recover the clique, I'm just going to think about this related question of whether you can tell the difference. Like I give you a graph and you just have to tell me, is there a planted clique? And this turns out to, in a lot of cases, be equivalent to the recovery problem. So for instance, in planted clique, it is equivalent. And here is the key idea of this low degree method, is that I want to look for a low degree polynomial that can somehow solve this problem. So by here, I mean a polynomial that takes in the entire input. So the input is like, you think of it as the adjacency matrix of some graph. So it's like, n squared different variables that are zeros and ones. And I want a multivariate polynomial that takes in all of these variables and outputs just a single number, a real number. And the hope is for that real number to be big if the sample was drawn from the planted model and small if it was drawn from the null model.
Is F supposed to approximate the distribution underlying either of the graphs?
Let's see. So maybe not exactly, but F is supposed to, the hope of what F does is that that if you give it a sample from the, so what it's really, we'll see what it's trying to approximate is really somehow the likelihood ratio between the planted and null models. So it's trying to output some big value if you're in P and some small value when you're in Q. But yeah, we'll see a bit later, a bit more precisely what it is trying to approximate.
Cool.
Yeah, so as sort of a proxy for this, right, I said sort of big in the planted and small in the null model. Here's more specifically the quantity that we're going to think about trying to compute. Okay, so it's a maximum over all degree D polynomials because we want, we want to find the best polynomial. And then this ratio is some measure of how well it's doing. So the numerator is the average value in planted, and you can think of the denominator as being like the fluctuations in the null model. So in order to succeed at this task, I want the mean in P to be sort of bigger than the fluctuations in Q. And sort of the idea here is that a lot of the best known algorithms can actually be approximated or represented as polynomials like this. And so we're using low degree polynomials as sort of a proxy for all efficient algorithms. Okay, so I've told you we're going to try to compute this thing in order to understand how hard the problem is of distinguishing P from Q. So this slide will be a bit of technical details of how you could actually hope to understand this quantity. Because naively, it seems pretty bleak, right? I have to maximize over all degree D polynomials, and it's really not clear how I would do that necessarily. But it turns out that this particular formulation boils down to a matter of linear algebra if you think about it in the right way. And so I want to think about this inner product between functions, which is defined by the expectation over Q, over the null distribution, and the associated norm. And then if I'm going to try to write everything in terms of this linear algebraic stuff. But in order to, the first step I need to do that is to take the expectation over P at the top and turn it into an expectation over Q. And that you can do by introducing a factor of the likelihood ratio. So the likelihood ratio of y, think of y as of the graph, is just like the probability that y occurs under P divided by the probability that y occurs under Q. Right, so that's just sort of a change of variables. But once we've done that, we can actually write the numerator as this inner product between L and F, and write the denominator as this norm. And suddenly now this looks like a problem we know how to solve, right? This is just, think of degree D polynomials as a subspace. So think of, you find a vector in a subspace that maximizes this inner product divided by its norm. And the answer is that F should just be should be L projected onto the degree D subspace, where the projection is orthogonal with respect to this inner product.
That's a very interesting insight.
Cool. Yeah, this was first developed by Hopkins and Stoyer, like the citation at the top, and among others in this line of work in the sum of squares framework. Right, so what we've learned here is that this thing we wanted to compute actually kind of has an explicit form. It's the norm of this low degree likelihood ratio. So you take the likelihood ratio and you project it onto low degree polynomials, and then you somehow take the norm of it in this as defined on the right. So this maybe sort of answers a bit your earlier question. The best F, the best polynomial, the best low degree polynomial to distinguish these two distributions is the one that sort of approximates the likelihood ratio the best. All right, so here was the conclusion from the previous slide. And sort of heuristically speaking, if this value is super big, that means there is a degree D polynomial that can distinguish quite well. Whereas if this value is not so big, say if it's only constant in the limit as n gets large, like the problem size gets big, this means that degree D polynomials are failing. And so this has been explored, and there's sort of a more formal conjecture along these lines now in the PhD thesis of Sam Hopkins. It says, for nice distributions, I'll talk about that later, but for a lot of these distributions P and Q, if this low degree likelihood is bounded when D is roughly log n being like the dimension of the problem size, then no polynomial time algorithm can distinguish. Right, so this is kind of conjecturing that the behavior of this thing actually predicts whether problems are easy or hard. Right, so informally speaking, it's saying that polynomials of degree roughly log n are as powerful as all polynomial time algorithms. Right, so maybe seems like a bit of a bold conjecture, but this actually holds up on all the standard problems we've looked at, like things like planted clique, sparse PCA, and so on and so on. I should maybe say, right, I've written this informal for nice P and Q. Roughly speaking, this means, you know, the flavor of these usual high dimensional type of problems we look at, which are kind of noisy problems that are highly symmetric with respect to all the variables. So I won't get too much into the details of like exactly what problems does this hold for, but it does certainly seem to hold for a lot of the natural ones. All right, so we might be interested, like, you know, sometimes we can show that this low degree likelihood ratio is small, and that suggests it should be hard, but can we really conclude anything, you know, rigorously from this? Well, one thing to point out is that in the case when degree is infinity, there is a rigorous statement here. So if you allow any degree, then having this norm of the likelihood ratio being constant actually does literally imply that no test at all can distinguish between P from Q. And this is sort of a classical second moment method. But that doesn't really address the computational aspects. Maybe a more relevant to our situation is that one thing that it shows is that if the low degree likelihood is bounded, for D being roughly log n, then no spectral method can distinguish P from Q. And by spectral method, I mean a pretty general thing. I mean, you basically get to build any matrix you like out of the data, as long as its entries are constant degree polynomials of the data. And then you basically look at the top eigenvalue. If this and threshold it, like if it's big, you say it's planted, and if it's small, you say it's null. The proof of this is actually quite simple, because by power iteration, you can just represent this spectral method as a low degree polynomial. The top eigenvalue can be approximated by taking the trace of your matrix raised to a reasonably big power, usually about log n. And this class of spectral methods are actually quite powerful in the sense that for problems, for a lot of these standard testbed problems we look at, like planted clique and so on, the best known algorithms really do take this form. And these are believed to be as powerful as the sum of squares hierarchy, if you've heard of that.
Mm-hmm.
Okay, so go ahead.
So just to confirm, if the spectral method fails, is that when we use the second moment method?
Oh, these two things. Yeah, so the two different things I mentioned on this slide are a bit unrelated.
Oh, right, they're different conditions. Yeah,
so the first one is just about if D is infinity, meaning I'm restricting myself to basically any algorithm that's not necessarily low degree. Mm-hmm. The second moment comes in that this is just how you, well, this norm of the likelihood ratio itself is sort of a second moment of the likelihood in some sense. And so this is why that's called the second moment method.
Cool.
Yeah, the point of this second one is this spectral methods is that, yeah, if you look at this norm of the likelihood ratio, whether or not this is big or not tells you whether or not spectral methods can succeed or not.
Totally.
So given, okay, so just to like summarize this low degree method, given some kind of hypothesis testing question, what you can do is take the degree to be about log n. You try to compute or bound this explicit quantity called the low degree likelihood ratio. And then if this is big, if it tends to infinity, this suggests that there should be a polynomial time algorithm. And if it's small, this suggests that there should not be a polynomial time algorithm. And this comes with some kind of rigorous evidence in the sense that spectral methods fail. So to say a bit about why I think this method is particularly exciting compared to like all the different options that are out there, it's actually possible to calculate this in a lot of settings, and it makes all the correct predictions for problems like planted clique, sparse PCA, and so on and so on. It matches, what the widely conjectured computational thresholds are. It's relatively simple to do the calculation, in particular, way simpler than the sum of squares lower bounds from which it was conceived. Another subtle difference is that this is really about the detection problem, whereas sum of squares lower bounds are really more about what's called the certification problem. It's very general in the sense we haven't made much assumptions on P versus Q, whereas something like the statistical query framework needs to assume that they have the form of IID samples. You can capture sharp thresholds like what's seen in the stochastic block model. And by varying the degree, you can also explore runtimes other than polynomial. So a more general form of the conjecture is that degree D polynomials are as powerful as algorithms of runtime n to the d, up to like log factors in the exponent. And this conjecture also holds up on the, all the standard problems that we've tried. There's no like ingenuity required in the sense that you just need to bound this explicit quantity. Whereas if you were trying to maybe do a reduction from planted clique or something, you would maybe need some problem specific insight. And finally, I think it gives kind of an interpretable reason for why some problems are easy and some are hard. Okay, so this will be one quick technical slide for those who want to see a bit more of the details of how you would actually compute this thing. I want to imagine this additive Gaussian noise model where I observe something that's y equals x plus z, where x is, I think of it as signal, which can be distributed in any way, any random vector or even matrix, and z is just IID noise. Okay, so we're trying to distinguish signal plus noise from just pure noise. Okay, so what do we do first? Well, remember we want to do this projection of the likelihood ratio. So the first step is to write down what is the likelihood ratio. So that's just for any given y, what's the probability y would occur under p divided by probability it would occur under q. And this is something you can work out explicitly using the probability density function of the Gaussian and so on. So you can get this explicit formula if you think about it for a bit. And then the key insight is like, okay, how do we project this onto low degree polynomials? Well, the way you need to do this is by taking an orthogonal basis of polynomials. So in this, with respect to Q. So in this case, this is what's called the Hermite polynomials, right? So we want to try to expand the likelihood ratio in this Hermite basis. And the reason for that is that the low degree norm just then becomes the sum of squares of these Hermite coefficients, of all the low degree Hermite coefficients. And so the problem boils down to how do you compute one of these Hermite coefficients? Well, and so the way you compute one Hermite coefficient is by integrating the likelihood against a particular Hermite polynomial. And using some nice facts about Hermite polynomials, it turns out you can actually compute this and end up with some reasonably nice expression for this low degree likelihood. So it depends on, it's sort of a sum, but it depends on this expectation over two independent draws, x and x prime, drawn from the signal distribution. Okay, so hopefully this gives you at least some flavor of how you would hope to do these types of calculations. So for more on this low degree method, you can look at the PhD thesis of Sam Hopkins, which in particular talks about the historically how it arose from sum of squares and so on. Or you can look also at this more recent survey article by myself and others where we present it more in the way I presented it here without needing knowledge of sum of squares. Okay, so this is now sort of a natural breaking point between the two parts. So the next part, which I think should be a little shorter, is where I will tell you a bit about what we can do using this method. So we're going to use this method to say something new about the sparse PCA problem. All right.
Awesome.
So let's see. So, okay, let's talk about what is sparse PCA. So I'll start by talking about the spiked Wigner model. So what this is a very simple example of kind of a signal plus noise situation in high dimensional statistics. So the thing you observe is going to be this n by n matrix, and it has a blue part, which is the signal, and the red part is the noise. So, okay, the red part, the noise, is just basically IID Gaussian noise, except that it's symmetric. It's a symmetric random matrix. And then the signal part is a rank 1 matrix. So lambda is just a number that tells you how big is the signal part. That's like the signal to noise ratio. And then XX transpose is this rank 1 part, where we think of X as being like this planted signal vector.
Cool.
And so I haven't told you yet what distribution X comes from, and that will be important. So at this point, there can be many different variations of the problem depending on how X is chosen. Right, so the goal is to, given Y, I want to estimate the signal X, or really the problem I'm going to focus on instead is just this distinguishing question of, can you tell the difference between the planted matrix or just the pure noise matrix Y? So I give you one matrix that's from either the planted or null distribution, and you need to tell me which one it was.
Cool.
And we are going to suppose that X is drawn from some prior distribution. So some examples of this could be spherical prior, which just means it's like a totally uniform random vector on the unit sphere. We could also imagine, for instance, that it has plus or minus 1 entries, just normalized so that it's a unit vector. Or what we'll talk more about is if it's some sparse, like if it's mostly zeros with a few ones. So, right, so we should think maybe a bit about, how would you solve this problem given this Y? And so a very standard technique is what's called principal component analysis, PCA. And that just means to use the top eigenvector and eigenvalue of the matrix Y. And so it's actually quite well known in random matrix theory exactly how well this performs. So in the limit of large n, you have that if lambda is small, so if lambda is smaller than 1, the top eigenvalue is 2, which is just the top eigenvalue of our random matrix. And more importantly, the correlation between the true signal and the top eigenvalue goes to 0. So that's like saying PCA will fail. Whereas on the other hand, if lambda is bigger than 1, the top eigenvalue is going to be something larger than 2, and there's going to be some non-trivial correlation between the top eigenvector and the true signal. So to summarize this theorem, there's like this sharp threshold where if lambda is bigger than 1, PCA succeeds, and if lambda is smaller than 1, PCA fails.
And the norm of lambda in the previous example, was that equal to 1, or was that the norm of X?
Back on the last slide, yeah. So lambda is a number. It's just a scalar number. So that's a good point. I'm always imagining the norm of X is exactly 1, just for normalization purposes.
Cool. Because I was wondering if that's a condition, then already we know PCA might fail because X would be equal to 1, given the...
Yeah, that's a good point that I have not maybe put that here. That yeah, I am assuming throughout this whole slide that the norm of X is going to be 1.
Cool.
Good. Okay. So PCA, works sometimes, but it doesn't really exploit the structure of the signal X, right? If we know something special about X, like sparsity, PCA is not really trying to use this. And so the natural question to ask maybe is whether PCA is optimal. So when lambda is smaller than 1, we know that PCA fails, but does that mean all other methods have to fail, or might there be something better than PCA? And so the answer to this question is that, well, it depends on the prior for X. So for a lot of sort of benign priors where X is just random on the sphere, or Rademacher, like if X doesn't have too much structure, then it turns out there's nothing you can do, that PCA is the best possible, And when lambda is smaller than 1, no algorithm can fail. No algorithm can succeed regardless of runtime. But some more interesting things will happen if X is instead sparse. And this will be the sparse PCA situation. So let's, here's a simple model for sparse PCA in this spiked Wigner model. So I'm now going to choose X to be a sparse vector. So K of its entries are non-zero, and those non-zero entries are just basically plus minus 1, except normalized correctly. And yeah, like before, I will always have X be a unit vector. And then I will take this spiked Wigner matrix like before, where the X is sparse. And the interesting regime for us here is going to be where lambda is smaller than 1. Because we want to look at in the situation where PCA fails, we want to ask whether there's a better algorithm that can somehow exploit the sparsity. Mm-hmm. And so let's think about, how would you try to solve this problem? So maybe the first natural thing to try for any kind of problem like this is what's called the maximum likelihood estimator. So let me define a few things. So this S sub k is just going to be the set of k-sparse vectors, Rademacher vectors. And what the maximum likelihood estimator turns out to be is that it just tells you to maximize this quadratic form V transpose YV over all sparse vectors. And take the V that maximizes this as your estimator. And so it's known that this will succeed, under some condition on the sparsity. And a different condition too, if you care only about the weak recovery problem. But, there's a big problem with this approach, of course, which is that in order to do this, you would need to do brute force search over all the possible sparse vectors, which will have a very slow runtime, right? There's n choose k possible sparse vectors. And so this is roughly, x of k, e to the k. Here I'm ignoring log factors in the exponent. Right, it's really something more like x of k log n, but I'll ignore the log n. Okay, so that's what the maximum likelihood does. But so now let's try to think about what's an efficient algorithm. If I want to do something that's polynomial time, what can I do? Well, this has also been proposed, and there's something very simple called diagonal thresholding. And what it does is it's very simple. You just take the largest k diagonal entries of the matrix and report these as the support of X. And once you know the support of X, it's very easy to then find X by, say, doing PCA on that restricted submatrix or something. And this is known to succeed under some other condition and has polynomial runtime. And there's also a variant of it that shaves off the log factors and does slightly better. Okay, so what's happening here? Why would thresholding the diagonal entries work well? What's basically going on is it's almost just a normalization issue, right? We've said that X is going to be a unit vector. And so if X is super sparse, like if most entries of X are 0, the non-zero entries need to be quite big when X gets sparse. And there's some point at which the non-zero entries of X become so big that they are just entry-wise bigger than the noise. And you're able to just pick them out easily. Okay, so let me just summarize what we've said so far. We know the problem is statistically possible when k is basically anything smaller than n, but the runtime is slow, is x of k. On the other hand, we know it's polynomial time solvable when k is smaller than square root of n, so when it's quite a bit sparser. And in between, it's widely believed to actually be hard. There's different reductions and sum of squares lower bounds that sort of indicate this. And there's a question of, the question I want to ask here is exactly how hard it is in the hard regime. So for instance, can you do better than this naive brute force x of k? The reductions from planted clique don't rule out, don't say much about this because planted clique can be solved in quasi-polynomial time. Okay, so the main, basically the main result that I want to tell you about is that we will show you that yes, that you can do better than exp of k, and we can tell you sort of precisely how well you can do. Exp of k squared divided by n. And I'll argue that this is actually, that first of all, this is achievable by an algorithm, and that also we believe this is the best possible thing you can do. So what's kind of going on here is that it's, it's easy when k is square root of n, and it's hard when k is n, right? So if I plug in k equals square root of n here, I get exp of 1, which is like a small runtime. If I plug in k equals n, I get exp of n, which is exponential time. So this sort of formula matches those two extremes that we know about, but it also sort of interpolates smoothly in between. So it's telling you, we know it's easy here, we know it's hard here, but furthermore, we know exactly how hard it is in between, and the runtime sort of like gradually increases as you go, as you make it more sparse.
Very cool.
Cool. And so let me, in the last few slides, sketch how we come up with this. So we're going to use the low degree framework like I talked about earlier. You will hypothesis test between this planted matrix and the pure noise matrix. And here's basically the theorem. We show that under some conditions, the likelihood ratio is small, suggesting that it's hard, and under other conditions, we show that it's big, meaning it's easy. And these are sort of both tight, like either the first condition happens or the second one. And so what it's basically saying is that degree D polynomials succeed when, either lambda is bigger than 1. We already talked about how that's PCA, and so that's sort of unsurprising. But more interestingly, it succeeds when D is bigger than k squared over n. And so from what I talked about before, this suggests that the best possible runtime should be e to the k squared over n, up to log factors in the exponent. So here we're kind of talking about sub-exponential time algorithms, so meaning e to the n to the delta, where delta is some constant, and I'm interested in pinning down the exact value of delta for any given choice of k.
Very cool.
So this already is sort of the lower bound, meaning that this theorem already tells you that in the low degree framework, you cannot do better than this. But what remains to be shown is that is there actually an algorithm that achieves this? And so, yes, I will show you that. I know we're getting a bit short on time, so do let me know if I need to wrap up, but
totally.
I guess I will.
10 minutes.
Okay, yep, we can definitely finish within 10 minutes, sure. All right, so let's think about the algorithm. So first, let's try to just solve the detection problem instead of the recovery problem. And so how it's going to work will be that you choose a parameter. So k, remember, is the sparsity of the vector, of the true planted vector. We're going to choose some parameter L smaller than k. And we're going to look at all the sparse vectors whose sparsity is L instead of k.
Mm-hmm.
And then we're going to maximize the quadratic form. So y is like the input matrix that we're given, and maximize the quadratic form over all v's that are L sparse instead of k sparse. And the algorithm is just compute that t and then threshold it. So if it's large, you output p. If it's small, you output q. For some appropriate choice of the threshold, which I won't get into. And so this algorithm actually sort of interpolates between the two existing algorithms that we know about. If I choose L equals k, this is just the same as doing the MLE, the exhaustive search. Whereas if I choose L equals 1, you can actually check that this is the same as doing diagonal thresholding. So this algorithm is somehow interpolating in between these two. And the runtime, well, you need to do kind of exhaustive search over all the L sparse vectors. So the runtime is basically exp of L instead of exp of K. Okay, but it remains to be shown that this actually works. So how would we show that this works? Under P, we're going to try to prove that this is big. And the way you can show that it's big is by take a V that's actually correlated with the true X and show that that will cause you to get a big value for the quadratic form. Whereas under Q, we want to show that T is small by doing sort of a union bound over all possible V's and show that they're all going to have a small value. The analysis is fairly straightforward. And what it ends up showing is that the algorithm succeeds so long as K is bigger, L is bigger than K squared over N. And this K squared over N you may have recognized from earlier, because this is exactly the runtime we were claiming, right? So if you choose the smallest possible L, you get runtime, which is exactly this exp of K squared over N. And so that's the algorithm for detection. It turns out you can also extend this to recovery if you're interested in actually finding the vector X. You start by just doing the same thing as before. So take U to be the maximum over the L sparse vectors of this quadratic form. But of course, U is not really a good answer because U is only L sparse and I want to find something K sparse. So I need to find a way to sort of clean this up to get the right answer. And it turns out you can do something very simple. You just take U and multiply it against your matrix, which gives you some other vector. And then you just threshold that vector. And it turns out this gives you a very good estimate of X. So it'll be exact recovery with high probability under those same conditions. Okay, a technical detail is that for these steps 1 and 2, you actually would like to have independent copies of the noise Y. But there's sort of a way you can clone the noise. You can take your original data and make 2 copies as if the noise were independent. And so just to summarize, I showed a continuum of sub-exponential-time algorithms for sparse PCA that interpolates smoothly between sort of the two that we knew already. So this diagonal thresholding and this exhaustive search algorithm. And so one way you can sort of interpret this is that, in real life, if I want to solve sparse PCA, but diagonal thresholding didn't work, and I'm willing to spend a bit more runtime, I can try, there are sort of these more advanced versions of the algorithm that I can try by taking higher and higher L to get a more powerful algorithm that also runs slower. So there's this trade-off. The result gives this smooth trade-off between sparsity and the runtime needed. There are a few extensions we can also cover, like if lambda is smaller than constant, or if you do the spiked Wishart instead of spiked Wigner random matrix model, or different, more general assumptions on X. And what I think is kind of interesting here is that we've really understood precisely what the best possible runtime is using this low degree likelihood ratio. Thanks, that's all.
Awesome, that was great.
Thanks.
Yeah, it's also really great that we know what the lower bound is supposed to be, and we also have a method of recovery. Because that,
gotcha.
Yeah. It can also be hard to come by, or at least for certain combinatorial processes. Cool. So I just want to clarify the distribution between either of the graphs. What do you mean by that?
Let's see. So are you talking about this planted clique that I talked about at the start, or the sparse PCA? Or which problem?
Yeah, the planted cliques.
Oh, okay. So for a planted clique problem, sorry, say the question again.
Yeah. When you say that there is a distribution on either Q or P, What do you mean by that?
Oh, let's see. So Q and P are just like the names of the two distributions. Like Q is the name of the distribution where the graph is just totally random. Each edge happens with probability 1/2. So that's just a pure random graph. And then P is the name of the distribution. So it's sort of this joint distribution where you first choose a place to plant the clique and you put a clique there. And then you also randomly choose all the other edges, each with probability 1/2.
All right, cool. So I believe that is all the questions that we have from the audience. Now, without further ado, I would like to thank Alex Wein for presenting his talk today. And if you guys like this video, feel free to like this channel as well as subscribe, and we will see you guys soon.
All right, great.
Xiang will let us know when we're off.